Hey, it's Jay, and today we have a bit of a different video. Normally, we go over a specific tool or process in Autodesk Inventor and teach you how to use it. However, today we're going over a specific skill that you're going to be using a lot on Cash Money, but it's way harder to learn than it needs to be, and we don't see why that should be, so we making a video on that. And that skill is constraining something like a wheel or bearing or something over a half-inch hex and locking down all 6 degrees of freedom.
Okay, so why is it so hard to constrain a half-inch hex bore to a half-inch hex shaft? Like in real life, it's trivial, and that real life is what makes it so hard because tolerances are a thing. Basically, they'll make it slightly bigger to allow for a little bit of, I don't know, screw up on both slight amount of manufacturing defects. That's the word on both the end of the bore and the shaft. And that makes Inventor really mad because it wants things to align perfectly, even though these only aren't don't line up by like a couple thousandths of an inch, which is nothing. So how are we gonna get around this? Um, the key here is to work off of one face of both the shaft and the bore. And the best and most consistent way I have found to do this involves two constraints that you absolutely have to use and one that's kind of optional depending on what you're looking to do. So I'm going to demonstrate this with constraining this bearing to this shaft. So first constraint you're going to need to do is mate. You're gonna use the mate constraint and mate a face of the bearing or the bore. This is the bore. It's whatever goes through the middle and you put it over the shaft to a face of the shaft. So that's a dumb thing, but it's fine. It's fine. That'll be a-okay. And we're gonna apply that. And now what that has done here is I locked down 1 degree of translational freedom, so I can't slide this way and this way anymore because this has to be next to that. And oh wait, no, that's gonna screw itself up. Hang on, because it doesn't like turning things once it's already done, once even though it's totally legitimate. Point is, it locks down 1 degree of translational freedom and 2 degrees of rotational freedom, because in addition to not being able to slide, it can no longer, so we're still going to constrain to that though, it can no longer rotate around the shaft, or it can't rotate up. And here, if I go to the right, it can't rotate this way or this way anymore either. And that's the key, is you're just trying to lock down all of the degrees of freedom, and that's what the idea of constraints. Okay, the second constraint is a bit picky. You have to remember what you used. So you can see I've got some degrees of freedom still. And the key here is you're going to constrain a corner axis of the face you've already used. So I got to get inside the bearing so that the bearing moves and the shaft doesn't. To a corner axis on the bore of the face that you've already used, because that allows you to get around the manufacturing tolerances. And you can see also I have 2 here. It's kind of relevant which one you pick. I just like to go for the one that's close to the face and not like around a little curve. So do that. And we can rotate back a little bit. Don't do that. And then we're going to click here. And you don't want it offset at all. You want it offset 0. And I should uncheck the predictive offset because that's the second time it did the same thing when I was practicing. Then I'm going to apply it. Okay, apparently I clicked the wrong thing. This is an example of what happens when the tolerances don't line up. It goes, I can't constrain this because this doesn't perfectly fit, and it gets really mad. So we're gonna, sometimes the best way to do this is just to full on delete it, the whole thing, and then start from the ground up again. Because sometimes it's just easier, because this is way harder than it needs to be. So again, we're gonna go ahead and we're gonna pick, it might have also been because of predictive offset. That could also be it. We're gonna pick that face, or any face really, and we're gonna pick a face on the shaft. and it'll constrain it to that. And now we can't rotate and we can't slide in that one direction as I've shown you. But what we can do still is slide in this direction so that we get some space, and we need to constrain it to this corner or the corner or this corner specifically because they're on the face that we've already used, and it won't have to deal with the bore being slightly wider than the shaft. So we're gonna do that, and we're gonna do that, and then it's like A-okay. Now we're here. And what that does there is it locks down the third degree of rotational freedom, so it can no longer rotate one of these ways. I'll show you. That's the wrong way. It can no longer rotate this way, and it locks down another degree of translational freedom, so it can no longer slide. So now the only degree of freedom that's still open is it can slide up and down the shaft, which is perfect and kind of what you want. So it's not inherently bad. You can leave it if you like that. However, if you're trying to be precise like you usually are in a lot of our like full robot CAD, I like to take a flush, constrain the top of the bore or whatever your thing is to the top of the shaft, and then just offset it whatever I want it, however far I want it along the shaft. So like 2 inches, 5 inches, it's A-okay. And sometimes the other thing to be aware of here is sometimes you'll have to, I think this works, sometimes you have to go negative on your offsets because it's a bit wacky. I think that's the, yeah, you see how I made 2 inches and it went down? I want to go negative 2 inches and it'll go up. So if it goes the wrong way, just make it negative. That's kind of how it works. Okay, so now we're just gonna delete this because we're just going to suppress. I did not actually use that constraint, but you got the idea. We're just going to suppress these two constraints and move on to the next example. We might not do that wheel. That wheel is very similar. The one thing you just have to watch out for here is this lip. You have to make sure you don't click the lip. You have to actually click inside of it because the lip is slightly bigger. So we're going to use this flywheel here for the next example, and we're going to go a lot faster this time because you, in theory, already understand a little bit. You'll notice the big thing here is it's got a triangular shaft. It's short 2 sides of a 1/2 inch X because it's only 3 sides. Now, this isn't a problem if you do it this way because you can just go, all right, I want this shaft, not this shaft, this face, and it'll stick them together. And you'll notice it's rotated because that degree of freedom is not locked down yet. And then once that's there, we can just go here and we can go, all right, now I want a specific axis or edge or whatever they are, the line. Yeah, I don't care if you're not saved. I'll save you later. Like right there. Click that and it's all okay. It's A-okay, it's all bueno. And then we're just going to make sure we click the right one here so we don't get Inventor really freaking out on us. I think it's this one. No. Damn it. So the key, sometimes it'll do this and it'll be all rotated and really annoying. And what you're going to want to do to fix this, I'll do this sometimes anyway, but it's not really necessary, is you'll pick something, you're going to basically go like, okay, I'm going to do this, and then you'll do it to the top and you'll set that angle to 0 degrees and it'll become flat, and it makes it easier to work with sometimes because now it's a lot easier to tell where stuff is. So now we can go ahead and we can try and go for the edge again, and you want to make sure you don't click the curved surface because that just won't work. Click that, then it's all lined up. And you could go ahead and you could do your flush if you wanted, but I'm not going to because I don't really care too much. I'll go for the home view because, yeah, now this will slide up and down, but this shaft is grounded in case you couldn't tell. You can see a little thumbtack. And it won't slide anywhere else. It won't rotate. All it will do is slide up and down the shaft. So, yeah, that is how you constrain 1/2 inch hex bores to 1/2 inch hex shafts. It's way more complicated than it needs to be, I know. I spent like a good couple hours trying to learn how to do this because it's an important skill. And yeah,